Okay, last week we stopped at the shear stresses. I think we covered a little bit about what the average shear stress means. Average shear stress is basically your applied load divided by the area. This is not the actual shear. When we get to the actual shear stress, we should have what we call the transverse shear stress. Might be covered this semester, might not be covered. But as far as average shear stress, which is represented by tau, our average shear stress equals P divided by A. Again, this here is a single shear, and that one here is a double shear plane on bolts. In other words, you see these two bars, C and D. Those two bars feel how much of this F? How much does they feel? How much do they see? Each bar of them will see the full F or half of F. Yeah, that's what you said at the beginning, yes. So each one of those will see F over 2. Each one of those guys will see F over 2. So this is what is explained here. So a double shear is beneficial because that reduces the amount of shear on each plane or in each section. But at the same time, it's more cost because you will require a longer bolt. You will require more plates, right? So in our design, we have to take care of how much we're going to pay or how much we're putting in the connection. Okay, now going further out, looking at bearing shear. What's a bearing shear or bearing stress, generally speaking? A bearing stress is, or it leads to one of the limit states, which is failure of the member itself. So I want you to imagine that this bolt was very strong. This bolt here was really strong, and it was able to take the shearing stress without failing in shear. Again, what's failing in shear? Meaning that the bolt itself would fail like this. Okay? So this is failing in shear, right? Now imagine that the bolt was very, very strong, and it leads to a compression force on this area of the plate that I would say deformed the area in front of it. Is this possible? Yes. So in other words, if I'm pulling on this sheet here out, my bolt is here, my bolt is very, very strong, I will end up cracking inside the metal itself. Okay? How do I calculate the stress that is applied on this part of my metal? This is called the bearing stress. This is called what? The bearing stress. Okay? So it's as simple as your P, the same P applied here, divided by an area. Which area is this? It's the area that it sees in front of it. So imagine that you're looking here. You will see a rectangle in front of you where the bolt is applying the load. So the bolt is here. Here's my bolt. This area behind the bolt where the bolt is pushing on is the bearing area. Again, let's think about the bearing as the compression by touching. So if I'm bearing on something, they even say bear with me. Like, what is bear with me? If this is the floor and this is something on the floor, the bearing stress is as simple as the compression stress. Okay, when somebody is bearing on something, he's just pushing down on it. Okay, so if the bolt is pushing on part of the metal, we take the area of this part as your area for bearing. And then the force being pulled is your force. Force divided by area gives you the bearing stress. Okay? So this is a very simple, another type of stress that we look at as well. Now, the type stresses that we looked at so far are tensional stresses, compressional stresses, shear stresses. Okay? Bearing stress is a compression stress, is one of the types of compression stress. Okay, keep going with the slides. We get to an example, a very important example. It has a lot inside it. One of the beautiful things about this example is it is in US customary units, which means pounds and inches. So it gets us also working with different units, so you can train yourself to be very flexible. Any type of problems you can solve. Now it says that the hanger shown, this here is the hanger. It has an upper portion of the link ABC, looking at the link. Again, the word link is very important here, and I will show you why it is important. ABC has a thickness of 3/8, and the lower portion has a thickness of 1/4 inch each. So this is 1/4 inch. The one in the back is 1/4 inch thickness. The one in the top is 3/8 inch. Okay, so there's two different thicknesses within the link A, B, C. Okay, and it says that the pin A is now the bolt. We're looking at the bolt now, is of 3/8 inch diameter, while the one used at C is 1/4 inch diameter. Determine the shear stresses at pin A. This is the pin, the shear of this bolt. The shearing stresses in pin C, this bolt here. And then the largest normal stress in the link ABC, the whole link. Normal stress is the axial stress. And the average shearing stress in the bonded surface at B. So how am I connecting AB to BC is through some type of glue. I'm bonding these two plates to that one plate using some type of glue. So I want to know what the shearing stress is at the interface between them. And then last, number E is the bearing stress in the link at C. The bearing stress at this place. Okay? So now the first thing we need to look at here is my free body diagram. I need to be able to solve and find forces within this problem. So if I'm going through this, I want to draw the free body diagram. I'll make this a little thicker. I'll draw something like this and something like this. Okay? Going here is a pin connection. Here is, I know this would confuse you more. I'll make it real pin. Here's a pin connection. Right? And here is a pin connection. Okay? Now another thing is that this here is also a pin connection. So I will open this up and make it round. Now, why did I make it round? Because this is a hinge. Again, how did I know it's a hinge? It's one bolt. If one bolt is attached over here, that means it is free to rotate. Free to rotate means pin connection. Pin connection means what? It means it only has the component of X and Y. Right? No moment. We agree on this? Okay. Let's now consider that this is true. That means I have X and Y here, and I have X and Y here, in addition to my force here. Do you guys agree? Very simple. But there is an added value to the word link. The word link, it means it will not take any force, and I will zoom out to show this on a side. It will not take any force except in its axial direction. That means the force here is equal to 0. The force here is equal to 0. Do you understand now? So any link that is straight, remember this. Number one, it's straight. Number two, it's not loaded out of plane. Not loaded out of plane. If these two happened, and of course number three is its pin connection. those three conditions happen to any member, that means it only takes which force? This force. Does that make sense? So automatically I'm looking at a link that is straight, that is pin-pin, that has no loading in out of plane. You see what out of plane means? Any loading that is like this. If I don't have those, this applies. There is zero out of plane force. Is that easy? What is this? Can you remember trusses? You guys took some trusses in statics. What makes the truss uniaxial? You cannot say that the force in a truss member there is X and Y. There's only axial forces, huh? What makes these axial forces? Because all truss members apply this. Pin-pin, they're all straight. They're not loaded in the middle of the member. You cannot load the middle of the member of the truss. Because in this case, it's not a link anymore. It's a beam. Now it must hold some moment, some bending stresses. But that's not what truss member is designed for. Okay? So let's make this clear. In this case, that means this here is actually a link. If this is a link, then which one of these 5 forces is gone? See, I have 5 red forces here. Which one of those 5 forces will not count? This one? This one will be 0? This one will count. Very good. So I will consider this. Let me see the names. So I will call this, for example, RA. What else will count? Let's say this is D. FDX, FDY. Do they count or not? FDX counts. FDY counts. We can assume going anywhere. Say this way and this way. Okay? What else? Of course, we have this X, this force, 500 pounds. Right? And then, how about this one? Does this one count? No, it's a 0. Why? Because this is a link member. So automatically I can say I will erase this guy. This one does not exist. So this here becomes my free body diagram. A, B is somewhere here, C is here, and E is here. Okay? Now, can I solve this? Very simple to solve, right? Now, what's the procedure to solve this? How can I solve? Can I solve it? Is it determinant, indeterminate? Is there a number of what's the number of unknowns here? 3 unknowns. What's the number of equations I have? 3. Sigma x, sigma y, and sigma moments anywhere, right? So which moment? Very good. So we start with sigma moments. Which one do we take the moments about? D. You agree? Everyone agrees with this? Sigma moments at D equals 0. So in this case I have RA times, so RA is going this way, yeah, consider this way is my positive. RA times what? 10 inches. Can you read from that distance? Up here. 10 inches. Plus or minus? Minus 500 times, it's about D. Very good, times 15. Everybody understands this? Equals 0. Okay? And then from this, solve for RA. RA equals what? 750 pounds. Okay, pounds is LB. Don't ask me why. Okay? So 750 pounds are here. Now, can I get FDX and FDY? Of course I can. Do I really need them? Did I ask for them in the question? I don't think so. Everything I'm asking for: shearing stress at pin A, shearing stress at pin C, right? Largest normal stress in link ABC, average shearing stress at surface B. So don't waste your time. If I'm not asking you for something related to D, don't bring it. Does that make sense? So now I got just the force at A, which is RA. Everything else is related to this guy. So I will just solve things in this guy. Let's continue to the next part of the, yes, we got 750 pounds. Correct answer using what Ola said. Sigma moment said G equals 0. What's my next question? It says find this shear stress at C. Is that right? Determine the shearing stress in pin A. Let's now look at A. Is A single shear or double shear? We have to think. Because if it's single, we take the force. If it's double, we take half of the force, right? Pin A is single shear or double shear? Single, right? You're confused. If you're confused, what do you do? And I want you to think about this. Look at the pin from the side view of the pin. Look at the bolt itself from its side view. Here's the bolt, here's the wall, and here is the link, right? The link is being pulled down. The wall is responding up as a reaction. How many shear planes is cutting on this bolt? 1. So it's a single shear. Okay? Now I decided it's a single shear. How do I get the shear stress? Do I have the force here? Do I have this force? Yes, it's RA. The link, the whole link has a force equals to that force. Okay? Now how much force is there? We said 750. If it's single shear, how do I get the average shearing stress? P over A. What's the A? A of the pin. You said the pin diameter is 3/8 inch, right? So, in this case, my tau of bolt A will be equal to P over A. That's equal to what? 750 pounds divided by the area of 3/8. Pi d squared over 4, right? So pi over 4, 3/8 squared. Is that simple? Very simple. We got the shearing stress here will be equal to 6790. This here is 6790 psi. What's psi? Pounds per square inch. Pounds per square inch. Okay? That's a stress unit. PSI is pounds per square inch. KSI, kilo pounds per square inch. KSF, kilo pounds per square foot. Okay? I just want you to get used to this. There is PSI, there is PSF, pounds per square foot, KSI, and KSF. Okay? K is kilo pounds, which is 1,000 pounds. Foot is how many inches? 1 foot equals 12 inches. Okay? These are basic things that I don't need to give you in the exam. How many inches is a foot? Is 12 inches. Okay? Now, the next question is find the shearing stress in pin C. Where's pin C? Down here. Single shear or double shear? Double shear. Now, confused. How do I know? Again, draw the pin. Here's the link coming from the top, right? This is pulling, this is pulling. And now I see here, this guy is going to D, and there's a pin here. So how many shears, how many planes of shears it's pulling on? 2. 1 over here, and 1 over here. So it is a double shear. Okay? Now, taking a double shear, that means my force is half of the force. Now, how about the area? We have to look at the pin C. Its area is also different. So in this case, tau C will be equal to P over 2 divided by A, which is 750 divided by 2. That's the area, that's the force, divided by pi over 4, but instead of 3/8 it will be 1/4 squared. Very good. I get a different value, and this value will be, where is it? 7640, right? So this here will be 7640 psi. Which one is higher? How come? Do you think a double shear would have less stress or more stress? What makes the stress in the double shear more than the stress in the single shear? It's the area of the bolt, right? You have an area of the bolt that is much bigger up on top. 3/8 is 0.375, right? A quarter is 0.25, right? And it is squared. So the squaring makes, so this is half squared, this is quarter squared, this is 0.375 squared. Okay? And it's not much of a difference. Anyway, what's next? Everything is clear so far? Now, the largest normal stress in the link ABC. I want you to remember that the link ABC is not one member. It has several sections. Okay? Let's take this on the side and decide, how do I get the largest stress? Now, does it have different forces along the member? Or it's one force? One force, which is the 750 pounds. Does it have different areas along the section? Yes, it does. Okay, if I want to get the largest stress, then I need to look at which area? The smallest area. Is that clear? Let's look, where is the smallest area of this guy? Let me erase this. It's okay. This guy here. Where would it have the smallest area? Again, it's not the side area, it's the sectional area. You understand what a sectional area means? It means you cut and look. Okay? Now here is what it says. It's 3/8 inch thick at the top and 1/4 inch thick at the bottom. And its width is 1.25 inches. Okay? In other words, my section at the top is this section, which is 3/8 by 1.25. Right? This is the section here. If I cut and look. Now if I cut down here and look, I will see what? I will see something else. I will see 1/4 and 1/4. Do you agree? I'll call this the top section. I'll call this the bottom section. Okay? Now this is what? 1/4, 1/4, and 1.25. Does it all work with you? Yes. Which means you have to take the whole hatched area. Are those the smallest section? Which one is the smallest of these two? Top or bottom? Top is smallest, right? I'm going to tell you no, not this. Why? Because there are holes. Where are the holes? This guy has a hole here, taken out from it. Right? And this guy also has a hole somewhere. One at pin A and one at pin C. Do you understand? So the critical place that holds the highest stress is the place where the holes are, which we sometimes call, when you go to steel section or steel design, you probably are taking steel now, it's called area what? Area net. You guys taking steel or you already took it? Exactly. Area gross and area net. What's the difference? Take the holes out. If you take the holes out, you get more critical areas. That means higher stresses. That's why when we design, we look where are our holes and how big are the holes to take out this area from my area, and that ends up with a higher stress. So I can design my member. So in this case, I have to look at the most critical section, which would be here and would be here. Okay? Those will be the governing ones. So in other words, when you said I'm comparing the top section to the bottom section, top section definitely has less area. Now take out the bolt width and calculate. And in this case, going down here, let's go to the last slide. Over here. Oh, this shearing stress at pin C. Largest normal stress here. In this case, I have the 3/8 multiplied by the 1.25, but I have to subtract what? The bolt width. Okay, why? Because my area ends up by being this and this. Does that make sense? So just add up those two rectangles together, here and here. That gives the smallest area. Okay? And in this case, you get the smallest area. You put it down here with your force. Now this is the normal, the highest normal or axial stress in the member. Last thing we're asking for is the bearing stress. Oh no, there's average shearing stress at B. It's another good question. Now, I have a member here, a member down here, and a member down here. You see here? I'm pulling up here. This is the reaction. Okay? This here is 750. Down here, it's 750 divided by 2, right? 375 and 375. Now, if I'm looking at the stresses along this, it was given that this here is 1.75, and the width of this whole guy is 1.25. Now, what is the average shear stress on this area? Now, I'm looking back. This is out of plane. If I'm out of plane, the thickness is 1.25. The height is 1.75. So this is my shearing area. So if I want the shear stress on this glue that pulls out the two together, it's just P, which is the 375, over A. Very simple. You divided by 2. My P is already divided by 2. Very good. So here is the P that is divided by 2. Each side takes 375. Okay? And in this case, he got a tau B equals 171.4 psi. The very last one, oh, I did not print it. And let's calculate it. If I'm looking at the bearing stress, where's the bearing stress? He's asking for the bearing stress at links in the link at C. You see where C is? What's the bearing stress over here? Your C looks like this. Right? Here's a bolt, and this guy is pulling up. Now the bolt wants to keep it down. So this here is the area I'm looking at. Right? What's the thickness of this? Thickness at C is here, this one, 1/4 inch thick. So it is out of plane, it's going 1/4 inch. In plane, what's the bolt at C? Also 1/4 inch. Okay? Again, خلينا نفكر فيها. This here is 1/4 inch diameter. If I'm pulling on this and the bolt is pushing down, I will be cracking this area. This area of the steel. This here is seeing some bearing. How much is the bearing stress? Force, bearing stress equals the force divided by the area. We said the area bolt multiplied by the thickness, right? So in this case, I say it's equal to the 375 pounds, because it's on one side. At B, it's double shear, divided by 1/4 by 1/4. Okay? And then you get the stress in PSI. Very simple. Just take the problem and look at it one by one. It gathers up for you all types of stresses we looked at. Maybe not the compression stress. But now I have bearing stress, I have double shear, single shear, shear on two plates glued together, and we have also the axial stresses. Okay?